Tabii şuradan şu düğmelerden açın. Bunlardan deneyim. Ben de hangisi bilmediğim için.
Ben direkt numarası yapıyorum.
Okey, olabilir. Okay, let us start. So today we are going to start by solving an example first. Let's write example. So we have a control system given in the following form. A unity feedback control system. And this G of S is given as 21S 13K divided by S squared plus 10S plus K. Okay? So in this case, this parameter K enters into the system at multiple points. And the question has two parts. The first part is really trivial with the Routh stability criteria. Determine the range of K for stability, for closed loop stability, of course. And the second part is going to be the aim of this example. So for K is equal to 10, find the number of closed loop poles satisfying real of S between 0 and minus. So now let us quickly look at the first part. So in the first part, of course, for closed loop stability, I need closed loop characteristic polynomial. And in order to be able to obtain that, I will write the closed loop transfer function. G closed loop of S is G of S divided by 1 plus G of S. And if I write this 21S plus 13K S squared plus 10S plus K divided by 1 plus the same thing. So now when I look at this transfer function, I see that the characteristic polynomial is going to be S cubed plus 10S squared plus I have KS plus 21S plus 13K. This is my characteristic polynomial, and I want this polynomial to have all of its roots in the open left-half plane. And that is going to give me S cubed plus 10S squared plus K plus 21S plus 13K. So this is a classical task of Routh stability criterion. We can just form the Routh array. So I have S cubed here, and S squared, S and 1. So here the coefficients in the first row will be 1 and K plus 21. And coefficient in the second row is 10 and 13K. Okay? Let us fill in the other rows. So I have in this row I will have 10K plus 210 minus 13K divided by 10. So this is going to be 210 minus 3K divided by 10 here. And here I will have just 13K. This will complete the Routh array. And I know that for stability, I need to have the first column of this Routh array to be strictly positive. Okay? And that actually means that this term should be positive. That means 3k should be smaller than 210 and 13k should be positive. Okay? Meaning that k needs to be larger than 0 and k needs to be smaller than 70. Okay? And that actually means that for the closed loop stability, the range of k is between 0 and 70. Okay? So now let us come to the second task. The second task is asked as the following. For k is equal to 10. For k is equal to 10, I know that this is in stability range. Okay? That actually means that for k is equal to 10, all of the roots are in the open left half plane. Okay? We are asked about the number of closed loop poles satisfying this inequality. So what does that inequality mean? It means the following. This is my complex plane, real of S, imaginary of S. I'm wondering about the closed loop poles, number of closed loop poles lying in this part here. Okay? So this point is -2 and this is 0. So we are wondering about the number of closed loop poles in this region. Okay? So here I know that, for example, we learned about Routh stability criterion, and the Routh stability criterion sometimes by the number of sign changes it gives us the number of some roots in the open right half plane. Okay? For example, if these numbers are plus plus, minus minus, and plus, then I know that the number of closed loop poles in the open right half plane is the number of sign changes. Okay? So somehow Routh stability criterion or this Routh array calculations, they are able to give us the number of closed loop poles which would satisfy this type of inequality. Okay? We know that Routh stability criterion can give us this type of, the number of closed loop poles which would satisfy this type of inequality. Okay? So how can we use the same criterion using the number of closed loop poles in this interval? So now the first thing that I'm going to understand here is that this is going to be done for k is equal to 10. Okay? For k is equal to 10, the characteristic polynomial is, so I have d of s in this case is s cubed plus 10s squared plus k is equal to 10, I have 31s plus 130. Okay? So my characteristic polynomial is here. And I know that this is inside the stability range for the closed loop system. Okay? For k is equal to 10, I know that the closed loop system is stable. The closed loop system stable means that all of the closed loop poles, all of the roots of this polynomial, they are actually inside the open left half plane. I know that all three roots are in the open left half plane. So here, I know that all three roots would already satisfy this part of this inequality. Okay? This part is already satisfied by all roots of this polynomial. Okay? So the only thing that I have to make sure that I need to find the number of roots which would satisfy the other part of the inequality. Okay? So I need to find the number of roots which would satisfy this inequality instead. Okay? If I know the number of roots satisfying this inequality, then I get my answer. Okay? So now the question is, how can I use the Routh stability criterion which gives us the number of roots for such an inequality? How can I use it for this inequality instead? Okay? So can I make some variable change in my polynomial such that when I use the Routh stability criterion, I know the number of roots which would satisfy this type of inequality instead of this type of inequality. Okay? So here let us try to do it. Since Routh stability criterion gives this answer for this type of inequality, I would like to define a new variable z. Okay? And for this new variable z, I will try to choose Z. I will try to define Z such that this inequality will be equivalent to this inequality. Okay? How can I define Z such that this inequality is equivalent to this inequality? So let us try to define our Z here. This is going to be a linear function. Okay? So here, and that is going to be S minus 2. Is this correct? If I use my Z definition given like this, do you think this would be correct? So here, where is the origin of the Z plane? Origin of the Z plane is at where? At S equals to 2, right? So here, but here I really do not want to do it. Origin of the Z plane, I want it to be at S equals to minus 2 instead. Okay? So how can I modify this definition? I'm just going to change this to this one. Okay? If I define Z equals to S plus 2, then this S equals to 0 or Z equals to 0 is equivalent to S equals to minus 2. Okay? So if I use this type of definition, origin of the Z plane would be here. And in the S plane, it is going to correspond to S equals to minus 2. This is going to be the origin of the Z plane. Okay? Then I know that this inequality in that case is going to be equivalent to this inequality. Okay? I will use this definition here, and from this definition I see that S equals to Z minus 2. Okay? So that means that into this polynomial I can substitute S equals to Z minus 2. So d of Z is going to be, I will substitute instead of S, Z minus 2. It is going to be Z minus 2 cubed plus 10 Z minus 2 squared plus 31 Z minus 2 plus 130. Okay? So suppose that this polynomial has a root. Suppose that this polynomial has a root at S0. Where is that root transformed in this polynomial? If this polynomial has a root at S0, where is the root of this polynomial in Z? Where do you think the root of this polynomial would be? Yes? S0 plus 2. So somehow this type of transformation would shift all of the closed loop poles by 2 to the right, so that when I apply the Routh stability criterion, then I would get the number of roots which are going to be inside this interval now. Okay? All of these roots are transformed into the right half plane, and in that case, if I apply my Routh stability criterion to that polynomial, I'm going to find the roots which would satisfy this inequality. So now all I have to do is actually to expand these polynomials, and here I will just write the result. This is going to be Z cubed plus 4Z squared plus 3Z plus 100. Okay? And then I'm going to apply the Routh stability criterion to this new polynomial instead. This is Z cubed, Z squared, Z, and 1 here. So I have 1 here, and I have 3, and I have 4 and 100. Okay. So here again, if you like, you can actually cancel the common positive terms here. I can write here 1, and I can write here 25. This is 3 minus 25. It is minus 22 divided by 1 minus 22, and the next number is going to be just 25. And when I now count the number of sign changes here, I see that there are plus 2 sign changes, and I see that in this case that means that 2 closed loop poles satisfying real of z larger than 0. Okay? 2 closed loop poles satisfying this inequality. Okay? I know that z equals to s plus 2. I can substitute it here, s plus 2. So this is going to be equivalent to real of s larger than minus 2. So somehow by transforming the complex variable, you can actually try to use the Routh array. So in this case, we are transforming the origin of the complex plane. By transforming the origin or by transforming the complex variable of interest, then you can use the same criterion for different purposes. Suppose that I have a polynomial d of s, okay? I know that Routh stability criterion actually counts the number of closed loop poles satisfying this inequality, okay? Suppose that I want to use the Routh stability criterion for counting the number of poles which would satisfy this inequality instead. Suppose that I want the number of sign changes to represent the number of closed loop poles with this inequality. How can I transform my variable? I need to define z equals to minus s. Okay? So if you want Routh stability criterion to count the number of sign changes for the number of sign changes to represent the number of closed loop poles satisfying this inequality, then you have to define z equals to minus s, and then you substitute s equals to minus z into your polynomial, and then apply Routh stability criterion and count the number of sign changes. It's going to give you the number of roots with this, which satisfies this inequality. So now this completes the topic of Routh stability criterion. The rest of the course today is going to be the so-called root locus. Okay. So now there are 4 topics left. One is root locus. Each of them is going to take approximately 2 weeks. So I have root locus 2 weeks, Nyquist stability criterion for 2 weeks. Border plots, 2 weeks, and state space representations, they are going to take 2 weeks as well. So here, especially during the Nyquist stability criterion and border plots, frequency domain design, I would actually recommend that you attend the classes. It is going to be root locus is one of the easier topics of this course, and it is intuitive, and you can also learn it by probably yourself. But when we come to the topics of Nyquist stability criterion and frequency domain design using border plots, everything will start getting quite non-intuitive. Okay, and learning about those topics by yourself without the classroom support, it's going to be much more difficult than learning the other remaining 2 topics. Root locus and state space methods, they are going to be easier and more intuitive parts of this course. But when we go into the frequency domain with the Nyquist stability criterion or the body plots, frequency domain design parts, you would see that everything is going to get quite complicated, and they're going to look like that these topics are from outer space. Okay, it's not going to be easy when we see those. But today's topic is not one of them. It is Routh locus. So here, each year I'm actually studying Nyquist stability criterion and body plots before I try to teach them. I start 1 week before trying to teach those. But this topic is not one of them. It is usually quite intuitive, and things are similar to what we have learned in the past. So here we are going to start with an open loop architecture, closed loop architecture here, given in the following form. Okay, so I have G of S, H of S given like this, and we know that the open loop transfer function here is G of S, H of S. Okay, that is our open loop transfer function. And in general, this open loop transfer function is going to be dependent on a single parameter, and it's going to contain some zeros and some poles, okay, D of S. So that is my open loop transfer function. It is going to contain a single unknown parameter K, and we will have the ratio or a rational function of the complex variable S. And then the closed loop transfer function is given as G over 1 plus GH, okay? It is going to be determined by this formula, and that means that the closed loop poles are going to be determined by the following formula. 1 plus G of S, H of S is equal to 0. Okay? This equation is going to determine the characteristic polynomial of the closed loop system. I can write the same equation as G of S, H of S is equal to -1. This is the same equation. And the next thing that I can do is that I can substitute this specific form of this GH into this equation. Okay? So 1 plus K N of S D of S is equal to 0, and this is going to give me the characteristic polynomial. D of S plus K N of S is equal to 0. Okay? So here, this equation is going to be extremely important for us. Okay? So here, K is going to be a single parameter, and as we change K, the root locations of the system are going to change. So the closed loop poles of the system are determined by this equation. Okay? And we see that in this case, they are actually dependent on this parameter K. Okay? So the task of Routh locus, this important method, is going to be the following. As K changes from 0 to infinity, we are going to look at the trajectories of the closed loop poles. We are going to be looking at the root locations of this polynomial. So we are going to try to draw the closed loop pole trajectories as K changes between 0 and infinity. So here, these closed loop poles are going to represent the root, and the trajectories are going to represent the locus. Okay? The name of the method, Routh locus, means that we are going to try to draw the closed loop pole trajectories as a single parameter K changes between 0 and infinity. So I'm going to start with a basic example first, and then we will get more and more complicated. So let us say that we have an example. So this is the example that we would like to draw the Routh locus for. So if I look at the open loop transfer function, g of s, h of s, in this case, this is a unity feedback system, so h is 1. So g is k over s plus 2. Okay? So if I compare this to this specific form here, I see that in this case, n of s is equal to 1. Because there is no 0 in this case. If I write this k times n over d, n is just going to be equal to 1. And d of s, in this case, is going to be s plus 2. Okay? So for this specific case, I have these selections. So now the task is to draw the root locus. If I substitute this d of s in this equation, it's going to be s squared plus 2s. And if I write k here, k and n there, it is plus k is equal to 0. Okay? If you calculate the closed loop transfer function of this system, it is going to be the same. I have k over s plus 2 divided by 1 plus k over s plus 2. Okay? If I write here the closed loop transfer function, it's going to be s squared plus 2s plus k. Okay? So it's going to give exactly the same formula as this one. This is my characteristic polynomial for this system. Characteristic polynomial is going to determine the closed loop poles of the system. So I'm interested in the closed loop pole locations of this polynomial. So where are the roots of this polynomial as k changes between 0 and infinity? Okay? I'm wondering about the location of the roots of this polynomial as k changes between 0 and infinity. So here I will find the roots of that polynomial. I can actually write it as follows. It is s plus 1 squared plus k minus 1 is equal to 0. So I have s plus 1 squared is equal to 1 minus k. So s12 is equal to minus 1 plus minus square root 1 minus k. Okay? So these are the location of the roots of that polynomial with respect to k. Okay? Now let us try to draw those locations as k changes between 0 and infinity. So I have real of s, imaginary of s here. So let us try to draw the roots. At k is equal to 0, maybe I should take this to a little bit to the right. So let us look at the root positions at k is equal to 0. At k is equal to 0, I have this term missing. Okay, so I have minus 1 plus minus 1. So the roots are at 0 and minus 2. So if k is equal to 0, the closed loop poles are at 0 and minus 2. Okay? So these 2 points are called the start points of the root locus. Okay? And these start points, we are going to show that they are going to be the open loop poles. We are drawing the trajectories of the closed loop poles, and we are going to see that the trajectories of the closed loop poles would always start from the open loop poles. And I see that the open loop pole here, the poles of this transfer function, open loop transfer function, are at 0 and minus 2. Okay? And I see that the closed loop pole trajectories start from 0 and minus 2. Okay? And as I increase k from the value 0, k is going to change from 0 to infinity. As I increase k from 0 just a little bit, if I make k, for example, epsilon, I see that these 2 poles are going to get slightly closer to each other. Okay? And then if I increase k a little bit more, these 2 poles are going to come even closer. Okay? So this getting closer behavior, it's going to continue until which k value? 1. So here we're going to see that until the k equals to 1, these 2 closed loop poles are going to approach each other, and at k is equal to 1, I will have two closed loop poles exactly at the same location. And that location is going to be the point -1. Okay? And this point is going to correspond to k is equal to 1, and this point is at s equals to -1. Okay? So we will have two closed loop poles exactly at the same location. And then what is going to happen if I increase k even further? If I increase k even further, then this number is going to be complex. Okay? So if k is larger than 1, then S12 is going to be -1 plus minus j square root k minus 1. Okay? In that case, we are going to start getting complex numbers as our roots, as our closed loop poles. So that actually means that as I increase k further, we're going to start getting a motion for the trajectories. It's going to be looking like this. The complex poles we're going to start observing, and then as I increase k, the imaginary parts of these complex poles will get larger and larger in magnitude. Okay? So this type of plot is called a Routh locus. Okay? It shows the location of the closed loop poles of the system as a single parameter of the system changes from 0 to infinity. Okay? So this type of picture would give us really a lot of information. So it gives us much more information than the Routh stability criterion. If I apply Routh stability criterion to that polynomial, what is that going to give me? It is s squared, s, and 1 here. So I can here write 1 and k, and here 2. If I complete this Routh array, I'm going to end up with k here. Okay? So in this case, in order to be able to make the first column positive, it is sufficient that k should be positive. So Routh stability criterion for this example is going to tell me that as long as k is positive, the closed loop system is going to be stable. Okay? So here, so why do we have closed loop system unstable for when k is equal to 0? When k is equal to 0, the closed loop system should be unstable according to that analysis. Why is it? Because there is a pole at the origin there. Okay? So, but for all positive k's, I see that both of the closed loop poles are in the open left half plane. Okay? And that actually means that for any positive k, my closed loop system is actually going to be stable. So this is the information given by the Routh stability criterion. But in Routh locus, we have much more information than that simple stability information. We could look at the performance measures by looking at the Routh locus here. For example, I can actually say something about the settling time of this system by looking at the Routh locus. So here, by looking at this Routh locus, what can you tell me about the settling time of the system as k changes between 0 and infinity? If k is 0, then the settling time is actually infinite because there is a closed loop pole on the imaginary axis. So the settling time is infinite, but as I increase k, these two closed loop poles would be approaching each other. In that case, what can you say about the settling time? Settling time is going to be determined by the closest pole to the imaginary axis. And I see that as I increase k, that closest pole to the imaginary axis is getting further away from the imaginary axis. Okay? And that actually means that settling time of this system is going to be decreased until k is equal to 1. Okay? Okay? What about afterwards? If k is larger than 1, what is going to happen? It's going to remain at a constant value, because in that case, I see that distance of the closed loop poles to the imaginary axis is not actually changing. Okay?
But
Yes?
shouldn't it have an impulse at the end? So, I mean, after a the cosine to reach at onun bir alakası yok.
Okay.
Yani settling time'ın sonsuz olma ihtimali de vardır yani cosine'dan dolayı ama onun geldiğinin bir alakası yok.
That cosine is always going to be decaying actually, or sine or cosine, because here the real part is going to bring us an exponential e to the minus t, and that means that these sines and cosines in the response will always decay. So here you cannot even say here what is going to happen here, for example, to the damping ratio of the system. So the system is actually overdamped until the value k is equal to 1. And at k is equal to 1, the system is going to be critically damped, closed loop system. And as I increase k above the value 1, the system now is going to become underdamped. And what is going to happen to the damping ratio of the system as I increase k?
Decrease.
It is going to decrease all the time. So here, if I look at the damping ratio, it is going to be the cosine of this angle. Or you can think about the extremes. If the angle is here, we have an overdamped or critically damped system. If the angle is here, then we have an undamped system. Okay, so we see that as k increases here, the damping ratio is going to get smaller and smaller. So this is actually going to tell us something. Although we have the same settling time for large case, we would see that the damping ratio is going to get smaller and smaller, making the oscillations more and more prominent in the response. Any questions here? So obviously, this is just an illustration for the Routh locus. In general, we are going to try to draw a Routh locus for much higher order systems than a second order systems. In this case, we could draw the Routh locus analytically, okay? But in general, for higher order systems, we are going to require some approximations, of course, okay? And in those approximations, we are going to try to solve equations of this form. And this GH is going to have some higher order terms, ratio of two large order polynomials, and then we are going to try to come up with a way to draw this Routh locus approximately. So here let us look at some interesting cases. If I have an equation in this form, s cubed. So forget about -1 now. Let us say GH is s cubed, okay? So instead of -1, I will put now 1, okay? Let us say I have this equation. How can I solve this equation? So, do you know what the solutions are? Tell me one solution. One. Yes, that is good. One of the solutions is at 1. Okay? So I know that is real of s, imaginary of s, and one of the solutions is 1. How many solutions are there in general? We're going to have 3 solutions, okay? And 1 is only one of the solutions. How do I find the other solutions? So here is what we do. Instead of s, I write this polar representation, okay? Instead of s, I write r, which is a positive number, times e to the j theta. And then I write the following. S cubed is going to be r cubed times e to the j 3 theta, and that is going to be equal to 1. Okay? And this 1 has also a representation. Its magnitude is 1, and its angle is, let me say, 0. Okay? And in that case, I can actually try to equate this magnitude with this magnitude and this argument with this argument. Okay? So I have r cubed is equal to 1, and I have 3 theta is equal to 0. Okay? So in this case, r turns out to be equal to 1, okay? And the angle theta turns out to be equal to 0. Okay? So one of the solutions has the magnitude 1 and the angle 0, which is just the number 1. How do I find the other solutions? In this case, I know that 1 is does not only have angle 0, but I can here add 360 degrees, okay? And in that case, you see that I have r cubed e to the 3 theta is 1, and I have 360 degrees, okay? So here I see that r cubed is equal to 1, and 3 theta is equal to 360 degrees, okay? Meaning that theta can be actually 120 degrees, and r is equal to 1. So the second solution, I can actually say that it has the magnitude 1 and the angle 120 degrees. Okay? So that actually means that the second solution is somewhere here. Okay? Where is the third solution? Yes, it's going to be somewhere here. And I'm going to obtain it. For example, you can, instead of 360 here, you can substitute minus 360. And that is going to give us a solution at minus 120 degrees or 240 degrees angle. Okay? So these are the solutions of this equation. So in general, on the right hand side, we are going to have a minus 1. Instead of 1, we're going to get minus 1. We can use the same logic in order to be able to solve that equation as well. If I have s cubed is equal to minus 1, in that case, I can do a similar thing. I have r cubed e to the j 3 theta is equal to, let us look at the polar representation of minus 1. So I have here minus 1, it has the magnitude 1, and the angle is 180 degrees. But here I can simply add k times 360 degrees. Okay? So it is exactly the same thing. So I can write minus 1 as 1, and 2k plus 1, 180 degrees. Okay? Here, sometimes I will be able to write the following. Here, it really does not matter if this is plus 180 or minus 180. So I can write here plus minus 2k plus 1, 180 degrees. So if I equate this thing to this polar representation of the minus 1, then I get r cubed is going to be equal to 1, and 3 theta is going to be plus minus 2k plus 1, 180 degrees. Okay? So I see here that r should be equal to 1. It's a real positive number. It should be 1. And theta is going to be plus minus 2k plus 1, 60 degrees. Okay? So it is going to be something like this. So where are the solutions of this equation? The first solution, let me say that k is equal to 0. They're at the angles plus 60 and minus 60. There are two solutions. Where is the third solution? It's the basic or trivial solution here. It is going to be, let me take this to be 3. Let's choose k is equal to 1. Then this is going to be plus minus 180. So the third solution is at minus 1. Okay? So here we see that this polar methodology, using the polar representation of these real numbers or complex numbers, might allow us to actually solve this type of equation. So in general, for g of s, h of s, we are going to have a much more complicated quantities. So, but here, I know that for that equation to be satisfied, g of s, h of s, it should be equal to minus 1, meaning that the magnitude of this thing should be 1, okay? And the angle or the argument of this quantity, g of s, h of s, should be equal to plus minus 2k plus 1, 180 degrees, okay? So in control theory, this condition is called the magnitude condition. And this condition is called to be angle condition. Okay. And I know that in Routh locus we have g of s, h of s given like this. Okay? G of s, h of s is k times n of s over d of s. So let us say that, for example, this g of s, h of s, it is k n of s over d of s. So let me say that this is k s minus z1, s minus z2. Let me say that there are n zeros, okay? And let us say that there are n poles. Okay? In this case, let us try to write the magnitude condition and the angle condition. Okay? If I look at the magnitude condition, k is going to be a real number between 0 and infinity. Okay? That actually means that the magnitude of k is going to be itself actually. Okay? So it is k. Magnitude of all of the other terms, they can be written as I from 1 to m, magnitude of z minus I, okay, divided by I have j from 1 to n, magnitude of s minus pj. This magnitude should be equal to 1 for solving the equation. For an s value, to solve this the equation g of s, h of s, is for an s value, to solve this equation, s should satisfy this equation. Okay? And then I will write also the angle condition. The angle condition is this thing being equal to this one. When I take the angles of multiplication of complex numbers, what happens to those angles? So, angle of s minus z1 times s minus z2, and what is the relations of the angle of the multiplication and the angle of the individual numbers there? If you have two complex numbers, s1 and s2, if you look at their angle, how can you write this in terms of the angles of s1 and s2? This is going to be just a summation, s1 plus s2. And if I have a division, if I look at the angle, in this case it's going to be subtraction, right? It is minus s2. So here I will do a similar thing. When I try to look at the angle of this quantity, it is going to be the summation of the angle of this one, angle of this one, angle of this one, minus angle of this one, etc. Okay? So here let us try to write the angle condition based on this. So k is a real number and it is positive. What is the angle of k? Its angle is 0. Angle of this quantity is going to be angle of s minus zi. I will sum this. I from 1 to n minus I have j from 1 to n, angles of the pole terms. Okay? This should be plus minus 2k plus 1, 180 degrees. Okay? So these are how our angle magnitude condition and the angle condition are looking like. So we are going to want to solve these two equations for s. Okay? And for an s value, to solve this equation, it has to satisfy both conditions for some k value. Let us give a break. We can start again at 43 past 4. 43 geçe tekrar başlıyoruz. Buyurun.